This video is the fourth part of the mini-series on autism and attention. We want to talk about a third cognitive theory about autism, which relates to learning. The general idea here is that greater information consistency is needed for learning, and hence people with autism would exhibit a preference for repetitive information, a tendency with restricted interest, and so on. Consider a recent study performed by Dr. Liz Pellicano and her colleagues using a realistic visual search task. Children were put in this room with lights on the floor, and one of the lights were pushed would turn red. And that's what the children needed to find. Without telling the children, the experimenters designed the room so that it's asymmetrical in terms of the information content. The target light has an 80% probability of being located on one side. Let's call that the rich side. Normal children, or typically developing children, were initially performing trial and error in the experiment. So shown here with these search paths, you can see they take a long path to find the target light. But after just a few trials, trial 17 here, they've learned the statistical information about the room, and they would deploy their attention accordingly. So on this trial, for example, a typically developing child would almost directly go to the rich side of the room. They wouldn't even search in the sparse side. In contrast, the children with autism were significantly slower in adjusting their attention on the basis of experience. They started out with trial and error, but even by trial 17, they still appear to be doing trial and error. These data supported the idea that there may be a deficit in children with autism in their ability to tune attention on the basis of experience. So they're slower at learning to attend. This fascinating study raises the question about why children with ASD required more trials to learn. The floor light search task is inherently complex. Successful performance depends on an ability to navigate a large space. In addition, other studies show that participants in this kind of setup tended to acquire explicit knowledge about where the light is often located, allowing them to develop the right strategy to search in the rich side first. If we want to understand whether children with ASD exhibit a general deficit in their ability to learn to attend, we need to design simpler tasks that do not involve spatial navigation or explicit strategies. Here's the task that my colleagues and I developed. We asked the children to search for a target fish. The fish is called Frankie, who is rounder and with scales, among distractor fish that are more elongated with stripes. All the fish are presented on a computer screen. Once the children spotted the Frankie the fish, they pressed the button to indicate whether Frankie was heading to the right or to the left. There was one and only one target fish on the display, and its heading direction was random. The child participants in our study performed the task for over 200 trials. For the first half of the experiment, we placed Frankie the fish in one quadrant of the screen more often than in the other quadrants. So these numbers here indicated, for instance, that Frankie was in the upper left visual quadrant 50% of the time. In the second half of the experiment, Frankie was equally likely to be placed in any of the quadrants at 25% probability. Importantly, we did not tell our children where Frankie the fish would be placed, so they would have to acquire this information spontaneously. As in our other studies, we tested children with ASD and typically developing children, matching the two groups on gender, age, and nonverbal IQ. On average, the children were about 10 years old and had an average IQ of about 108. Here are data from typically developing children. We plotted their speed, this is in milliseconds, in finding the target fish in the training and the testing phases of the experiment. You can see that in the training phase, typically developing children were faster finding Frankie when it appeared in the high probability quadrant, labeled here as rich, than when it appeared in the low probability quadrants, the sparse quadrants. In the testing phase, when Frankie appeared in random locations, the advantage in the previously high probability quadrant gradually disappeared. If children with ASD required more evidence for learning, then they should take longer to develop an advantage in the rich quadrant. However, this was not the case. Children with ASD were slower in their response initially, you can see here, compared with the typically developing children. However, the difference in the search time between the high and low probability quadrants appeared just as quickly as in comparison children, and the magnitude was similar as well. In addition, children with ASD also adjusted their attentional preference for the high probability locations relatively quickly in the testing phase. These data do not support the idea that a general deficit of learning underlies ASD, or that greater information consistency is needed for learning. This concludes part 4 of the mini-series.